Welcome to Ask and Learn.
So in this question, we pretty much have to redo example 12. And since example 12 is a very lengthy example, I put it here just as a reference so that firstly you can see all the numbers from example 12 and the graph from it, and second you can compare how this question differs from example 12. Because in example 12, you disconnect the battery, and in this case, you leave the battery connected. And I think the main difference is that if you disconnect the battery, the voltage of the capacitors is free to change, but the charge will remain the same. If the battery remain connected, then the charge can change because the charge can flow from the battery or to the battery, but the voltage remains constant. So that is the main difference between this question and the example 12. So by leaving the battery connected, the voltage does not change when the dielectric is inserted, but the charge will change. And because the charge changes, the electric field will also change. Let's just walk through part A to H together with problems. Part A, what is the initial capacitance? Let's work it out. But part A is 1 picofarad because the initial capacitance does not change. It's the same as here. And in part B, what is the charge on each plate before the dielectric is inserted? Still, it's the same as the example because nothing's changing because we haven't done anything to the capacitor yet. Is then part C. So what is the charge introduced on each phase after it is inserted? Okay. So there are part C to part the newly introduced part H. I think because we are solving the whole thing in a different manner now, because we are assuming the charge does not change, but the charge will be changing and the voltage remains constant, we will be doing this question in a whole different way. So the way we answer the question might be a little bit out of order compared to the original example. So we will be answering part C to part H together. So first, I think the very first thing we need to do is we need to find the electric field of it. So the initial electric field, so this is really part D that we will be doing first. What equals, so in order to find the electric field, the voltage is constant, so we have V equals electric field times D minus L. This is a part without the dielectric, and then the part with the dielectric is L, ED. So, and ED equals E naught divided by K times L. This gives us E naught equals ED equals let's find E naught since that's easier. E naught equals V over D minus L plus L over K, which is 150 volts, over 2 millimeter minus 1 millimeter plus 1 millimeter divided by 3.5. This is 1.167 times 10 to the 5th volt per meter. And then if we know E naught, we can find ED. because it's just this divided by 3.5, and this actually answers part E for us. And then we can actually also answer part H, because it's, now that we know the electric field, it's so much easier to find the charge from the electric field. So that's why I altered all the order of this question, because it's easier to find the charge from the electric field using Gauss's law. And then from that, we can go back to part C and find the induced charge. Newton times meter squared Newton r. Okay, so 2.582 times 10 to the negative 8 coulomb will be the induced charge. Will be the total charge, and then we go back to part C to find the induced charge. Induced charge is the total charge times 1 minus 1 over k, which is 2.582 times 10 to the negative 8 coulomb times 1 minus 1 over 3.5 equals 0.84 times 10 to the negative 8 coulomb. So that is part C, A, B, C, D, E. We need to do part F and G. Part F, because battery voltage does not change, the potential difference between the plate is unchanged. It's still 150 volts. Part G, capacitance, is Q over B. So it's 582 times 10 to the negative 8 coulomb over 150 volts, which is 1.72 times 10 to the negative 10 picofarad. And of course, this is no surprise. This is the same as what we found in the example, because whether the capacitance is connected to the battery or not does not change its capacitance.